Okay, we start up again. The next thing we are going to look at is what's called classification of this didn't look too good, did it? Just blanks. Okay. I think it's in there, it should be. Anyhow, if you look at the material you have been given, you have several blocks of these finite difference I put out for you. Actually, starting with the second, which is covering the classical way to classify partial differential equations. It's written in Norwegian, sadly, but I mean, you find this in any book. You also find it in this book by Vertiger, which I was trying to show you, but he writes it a little bit brief. So I'm going just to have a peek into it here, what we are talking about. So here you have a general second-order differential equation, partial. And we have an unknown variable phi. We don't know what that is. Could be a scalar, could be a vector. It doesn't really matter. So what's important here is the double derivative terms and the coefficients in front of them. And for us, we will have a sort of a quasi-linear version here of a partial differential equation looking at the Navier-Stokes, where, as you know, you have the double derivative when it comes to the viscosity. But we have some nonlinear terms. We have some function multiplied with the derivative of functions in the convective terms. So it's a nonlinear differential equation. But now, how to classify an equation? Then we are using the characteristics. So you sort of rewrite your equation as a first order, a system of first order equations, and looking at the different characteristics and how they look. Here is a little mathematical. So we don't really need all this discussion. But in the end here, the three coefficients, A, B, and C, it's a question whether you get some roots from the characteristic equation, whether they are real or complex. And also an option, you have just one single root. So the names that people then have invented, they are hyperbolic, elliptic, and parabolic. These names are taken from math. I mean, taken from cross sections of a cone. So they don't mean anything physically. But here, whether our equation, whether it's hyperbolic, elliptic, or parabolic, or a mix, is very important for us. We have to know it in order to achieve a solution. So we are going to address what this implies, especially then when it comes to the boundary conditions. That is what's important for us. This way of deriving what type of equation you have, what family it belongs. It's nice when you have a second order equation. When you have a first order, you can't really use this setup at all. So you sort of have to know where your equation belongs. Of course, with a little training, you will get the idea. But here, to set it briefly, for a hyperbolic system, you have two real characteristics. Elliptic, you don't have any real characteristics, just imaginary. Parabolic, you have one real characteristics. So now let's see what this means for the boundary conditions. So you have some examples here, so you can have a look if you like. I'll go through these effects that we have here, the implications for us, so because that is important. So that one we have to look into. So let's start with a hyperbolic problem. Focusing here on boundary condition and initial conditions. Yeah, well, we can say this one first. Boundary conditions. We have different types of boundary conditions. For any equations, we have an unknown quantity, a little u. It doesn't have to be velocity, it could be anything. But now assume we have an equation for our quantity u. If this one is given on the boundary, we know the value on the boundary, then we call it a Dirichlet condition. Dirichlet condition. If we don't know the quantity itself, but we know something about the derivative, say du dn, where n typically then is perpendicular to a surface, to the boundary. If that one is given, and here n should actually be a vector, but normal direction. If this one is given, we call it a Neumann condition. So typically one of those two will be used. Neumann condition, Dirichlet condition. Think of it as Dirichlet is given directly. Neumann, then you have the derivative. And here it could be second order derivative, third order derivative, whatever. Doesn't have to be just first order. Any derivative will do. Still called the Neumann condition. Then also you are talking about a Robin condition. Robin, that will be both of them at the same time. Quite rare. You might find some physical problems where you use both of them on the same boundary as a mix. So you have given some sort of a mix of u and the derivative of u on the boundary. Okay. I never used it, but at least the name you should be aware of, the Robin condition. Let's start as first case, the hyperbolic case. Hyperbolic equations. And as a classic example here, double derivative with respect to time equals, and then we have some a0 square, which then is the speed of sound, and then a double derivative with respect to x. So that's a one-dimensional wave equation. That one is hyperbolic. It has two real characteristics. Characteristics will now be dx dt will be plus or minus a 0. So this is our equation, and we want a solution. And here I have a region in space, x. And up here I write time. So initially time equals 0 or some value, we know our quantity only at a certain range here in x. So this will be the initial value, initial data, initial conditions. Then here we know the quantity, of course, or else we can't get started at all. So here our unknown is given. Now what happens physically here? The information is going to travel along these characteristics. And if it's a linear equation, A0 is constant, meaning a signal here from this point is going to spread out in space. And in this diagram, he's going to move at a straight line like this. So here you have the characteristics, dx dt equals A0. So the information will spread out. That will happen to every point. Every data that we have here will do exactly the same. Also, the leftmost point, he will also spread out something like this. So now we can ask, where can we now find a solution? Well, the initial data that we started with, they are going to have an effect. They're going to influence the solution for this entire sector. So this will now be my influence area. Influence area. The entire sector. But I can't find a solution, a complete solution inside that entire sector. That's not possible. So given the problem here, you can only find a solution inside this cute little triangle. This is my solution area. Because if you go outside this solution area, any point, then okay, we have some influence at this point, somewhere down here from our initial data, but we are going to miss wherever comes from the left. We don't have that information, hence you can't get a solution. So you can only have it in this cute little triangle. And for a nonlinear equation, A0 is not a constant, it can be a function. It could be a u square here if you really have a nasty equation. Then these lines, okay, they will not be straight anymore. They can be curved as well. So this can be a little pain if you have a complex geometry. Say in the xy space here, if you have a wall, something like this, and then the characteristics, they will sort of spread out from all the points here, but actually down here as well. So what's happening here and here, going through the material or whatever. So there you have to pay attention how to handle the boundary conditions here. Of course, if this region in space were enclosed, say you had a solid wall here or something, up here, solid wall, then we could expand our solution area, because then any information, any wave traveling here, hitting the wall, he will reflect and go into our domain again. So there you can have boundary conditions alongside a solid wall. If it's an opening, a tube that opens to the atmosphere, for instance, then again we need to know something about what's happening here then. Typically you will use something like this, derivative equal to 0 or something for an outlet. Then again we could expand our solution area to cover the entire distance x if we know something about start and stop here. Any questions to that one? That's okay. The next one, elliptic. Example, we use the Laplace equation, double derivative with respect to x and respect to y equal to 0, Laplace. So that's a classic elliptic equation for you. Here I need a solution in space only. Time does not enter the equation. Of course, one of these could have been time. That's okay. Still an elliptic equation. So whether it's time or space, that really doesn't change anything. But here I use x and y. More easily understandable, and also that's what we're going to use later on. Elliptic in space. So you want to find the solution in a region here, like that. Then you are going to need boundary conditions all around the entire surface. Here the information doesn't travel along any characteristics. Elliptic, you have no characteristics. So if you change a value on the surface, on the boundary here, you change it a little bit, the entire domain feel it sort of instantly. So this one, you'll have the influence and solution area will be the same. And physically, this can be a pain, and it can also be dead wrong. Imagine you are doing incompressible flow, and we are looking from an oil platform where they have drilled a hole, and then we are pushing oil, liquid, from the North Sea all the way to England, 400 kilometers. And then we say the volume flow is huge. I mean, these pipes are 1 meter in diameter, can flow pretty fast. So then they all of a sudden they say in England, we don't have space enough for more oil. Stop it. So they close here. They close the pipeline. 400 kilometers. What's going to happen? Well, if you're using incompressible flow, then the information travels instantly, faster than the speed of light. So all of a sudden, that information should be detected 400 kilometers away. That's not possible, of course not. What's going to happen is that you don't have an elliptical system. The information is traveling with the speed of sound all the way up here, and then finally here they will then understand that okay, something has happened in England, they have closed the system. Then the fluid will start to slow down here. But of course, if they do it like that, you will smash any vent, any valve, or whatever they do, because you have quite a lot of momentum still moving. So using an elliptic description with an incompressible flow here, that's not really physical. But that's what you do when you say incompressible flow. You get an elliptic physical domain. And changing any value here will sort of be felt instantly throughout the entire domain. But to obtain a solution, you have to say something about your unknown. You have to either give him as a Dirichlet condition or a Neumann condition around the entire boundary to be able to obtain a solution. You can't skip a little part here. That's not possible. You have to say something of, for your unknown. The last one, parabolic. Parabolic flow, we use a one-dimensional diffusion equation. Time derivative equals double derivative with space. That's a 1D diffusion equation. Here we have one real characteristics. So how can we solve a problem that is parabolic? Well, it's a one-dimensional problem. So I have x, and I have given a region in x where I now have initial data, initial condition. Then I want to solve my unknown in time. How can I do that? Well, you are going to need boundary conditions as well. So here you have to specify what's happening to the left and to the right of your region. Here you need boundary conditions. And to find a solution, you are dependent on the history. So if you are looking at a solution here, well, the characteristics, that will be the velocity will be infinite in at one certain time level. So this will be the characteristics, just a horizontal line. And if you know the solution here, then you can march your solution forward in time. So you will always be dependent on the previous history of your problem. So again, the influence and solution area is identical. As a little hint, the elliptic, he didn't have time. Hyperbolic, parabolic, they both had time derivative. But don't narrow yourself down to say, okay, parabolic needs time, hyperbolic needs time. That's not necessarily the case. Like for instance here, a parabolic problem. Can you imagine a physical problem which is parabolic? You march your solution forward, but you don't have time in the problem. You only have space. Any suggestions? A parabolic equation, marching your solution forward. Look at this problem, for instance. Blasius, you're sending in a constant velocity. So there you will then have the boundary layer equations. They are parabolic, not in time, but in space. So the boundary layer that's going to grow here. How do you find a solution? Well, if you have a solution at one point, you know the velocity profile here, like that. Then you can find the solution at the next step, and so on. So here you march the solution forward in space. So parabolic, but you don't have time in the equations, you only have space. So yes, you can find some physical problems where you have parabolic or even hyperbolic, but you don't have time in your equation. That's possible. Okay, so the classification that's here taken from this number of characteristics that we have with this second order classification scheme type, but we are going to see hyperbolic equations, for instance, looking something like this: du dt plus velocity du dx equals 0. That's the advection equation, hyperbolic. It's only the first order equation is still hyperbolic. Or the continuity equation, time derivative of rho plus divergence rho u equals 0. That's also a hyperbolic equation, although only first order. So these, they don't really fit into the system. So you don't find two characteristics here. Well, you can say this A could be positive or negative, but they don't really fit in. You just have to know it. Yes, these are also hyperbolic in nature. Okay, any questions? That's okay. Please feel free to interrupt me anytime. So if you have a question, just interrupt me. That's quite okay. So this is something that we really have to be aware of when we are dealing with partial differential equations. What nature does it have? What do I have to think about when it comes to the boundary condition and also the initial conditions? What do I need to obtain a solution? That's important. Yeah, let's do it like that. Yeah, they're talking about a well-posed problem. So if it's elliptic, okay, then you have to use boundary conditions continuously around the entire control surface. Parabolic has to be open in the marching direction where the solution sort of has to be able to evolve. Hyperbolic, again, open in the evolution direction. And we need initial data enough so that we cover the area that we want a solution in. Okay, back to the first finite difference and the equation system that we are going to address, the entire Navier-Stokes. Some authors use the Navier-Stokes. There's only this one, only Newton's second law. Others say the Navier-Stokes, that's the entire set, both continuity, momentum, and energy. Your choice. Just be aware that people use it differently. Here, they're sort of written in a quite general form, so it can be compressible as well. Density can change. I even have just the viscous stresses here. I haven't specified Newtonian fluid, could be non-Newtonian as well. And the energy, I have some enthalpy here, and the thermal conductivity doesn't have to be constant. So definitely complex set of equations, highly nonlinear inside these total derivatives here and here as well. So quite messy, and also it's strongly coupled. You can't just take one of them and solve it. Everything has to be solved at hand, and if you start counting the unknowns, How many do you have in general? Well, you have 1 for the density, 3 velocities, and 1 pressure, that's 5. And then here we have enthalpy, and we have temperature. So we are missing some equations here. The system is clearly not closed. So to close it, you're going to need some state equations, ideal gas law or something, to couple this to close the set, to have enough equations for your unknowns. Now I want to simplify. And now incompressible flow, viscosity is constant, then they simplify a lot. So the continuity now only says divergence equal to 0. Momentum equation now with constant viscosity in Newtonian fluid. And for the energy equation, you can express it only with the temperature. And now the last equation is not needed, actually. This one is not influencing these two. So you can solve these two alone. Then you can solve this one later if you want to. But it's not directly coupled anymore. So how many unknowns? Now the density, it's just a parameter. So you have 4 unknowns, 3 velocities, and 1 pressure. And here, these 2 equations actually are 4 equations. Remember, this is a vector equation, 1 in each direction. So here you'll have 4 equations with 4 unknown, enough to close the system. Okay, so now the question is, are they parabolic, elliptic, hyperbolic? What? You can't really tell. You can't really see it directly. To see it, you do a little exercise and simplify even further. Of course, in this simplification will not be so physical. We're saying that this energy dissipation function is 0. It's very small anyway, so that's not a big deal. But this one, of course, that's not correct. But here it's just to illustrate or find the nature in the equation. So I remove the total derivatives, only use the time derivatives for it. Well, equation 1 reads as before, divergence free. Newton's second law simplifies, only time derivative here. And the energy equation also simplifies, been removed the last term, and also the total derivative becomes time. The last one, that's a parabolic equation. 1 time derivative, double derivative in space. That's parabolic. These two you can't see directly, but take the divergence of the equation, then this one, the divergence of this one, well, divergence of velocity is 0, divergence of velocity is 0, so they disappear, is constant. Divergence of that one disappears, and you are left with Laplace equation. So there you can see the elliptic nature inside the equation. You have to take the divergence of it. Or you could take the curl of this equation. Then you will have a dynamic equation for the vorticity. And this one is parabolic. So you might say, in general, when we started out here, for the entire Navier-Stokes, actually has hyperbolic nature, elliptic nature, and parabolic nature. All 3 is represented at the same time. Fairly tricky, to say the least. So now, depending on how you simplify your problem, if you jump to incompressible flow here, then you lose the hyperbolic nature. Nothing here is hyperbolic. So here it's elliptic and parabolic, not hyperbolic anymore. Okay. Next, we are going to address the finite differences a little bit. You should have touched some numerical theory in advance before you came here. So I assume this one should be fairly familiar for you guys, using the Taylor series to construct different numerical schemes for the different derivatives. So here you will have a positive step, here a negative step, and then you can start playing around with these two series, add them together. You can find a double derivative, an expression for the double derivative, which then is second order accurate. Subtract them, then you can find a first order derivative. Here again, second order accurate. You can use forward difference, backward difference. So we are going to play around with these different schemes, sort of as building blocks when we construct discrete versions of our equations. Yeah, let's do a little notation before we take another break. Notation. So this is going to be messy. We are taking material from different books. We are addressing numerical schemes, discrete equations, but all of a sudden we are also using tensor notation. So you have to be quite careful what we are looking at. Let's start with a simple finite difference description. So here I have a region in space, x and y. And what we are going to do now is to create a mesh system, nice, regular, like this. So we have a delta x and we have a delta y, and they don't have to be constant. They can of course vary, but for simplicity, think of them as constants, like that. So then we are now seeking a solution at certain discrete points. Could be the corners here in this grid system that we want to find the solution here. Then we can specify the positions by using indexes. So here in the x direction I will use I, in the y direction I will use j, in the z direction k if necessary. So that means for an arbitrary point inside, say this one, that's point I comma j. If you want to find the position, then you take the number I, the integer, and multiply with delta x, then you have the x position for it. So if I now want to have something like the x derivative at what point? Say point I, j. How will I write this one? Well, if I want this central space scheme, second order accurate, then you need the two neighboring points on each side. So you're going to need u at point I plus 1 j, minus u on the other side, I minus 1j divided by 2 times delta x. If you want double derivative at the same point, double derivative of u at the same point, we say this one equals u I plus 1 j minus 2 times the center point ij plus u I minus 1 j divided by delta x square. These are central space in central space schemes, meaning they are second order accurate here. Delta x square, that's the added delta x square. If I now want the time derivative, I want du dt in the same location. How do you write that one? Then for time I use superscripts. So this one I will write something like this, ui comma j, and then I use n plus 1 for the new time level, minus ij at the old time level n divided by 1 delta t. So these are typically what I will use to construct my discrete versions of partial differential equations. This is a first order in time. So we call it an Euler scheme, first order Euler scheme. It's the first one you will try typically. It's the easiest one, and on the right hand side then you will have only old values, so it's a pure explicit equation system, very easy to solve. So typically that's where you start. Later we will address implicit methods, looking at higher order in time as well, but more of that later. So this now will be the sort of the standard notation that we are going to use. Just be aware of something that is called tensor notation. That's also something widely used, and also we are going to address it a little bit. There you have the option of writing partial differential equations very compact, but then these subscripts mean totally different things. Like for instance, u I comma I, what's that mean in tensor notation? Here the indexes I, j, whatever, index means say x, y, z, or even time. That's also an option. So when you have an expression like this with an index, this means either 1, 2, or 3, or x, y, or z, meaning the velocity in the x direction, velocity in the y direction, and the velocity in the z direction. When you have the same index twice in a term, that means you have to sum them together for all different indexes. And when you have something after a comma, that means take the derivative of it. So this one actually is the same as to say du dx. Then I take in the first one, meaning x and x, plus, and then say 2, 2, or in the y direction, it will be dv dy, and the final dw dz. So that means, yes, you can write equations very compact with this tensor notation. So we are also going to encounter this one from time to time, so just be aware I'll try to point it out whenever we meet them, but I might forget. So please, then you just ask me: is it tensor notation or is it the indexes for a numerical scheme? One might easily be confused here, of course. So tensor, you have the same index in a term. Add them together. If you have a term reading something like this, uij, well, then you just keep him like that. So this could then be the I component of the Navier-Stokes or whatever. So here you can't really do anything else. You just have to be like that. Not everybody is using this after the comma, meaning derivative, but you may encounter it in some books. Okay, any questions? Then we take a break.